Okay, and we're live. All right, so review of the force unit. Remember we started this unit out by doing a bowling ball activity in the hallway, the bowling ball obstacle course, and we kind of learned two surprising things. One, when it was in the no-touch zone, it pretty much went the same speed. And two, to make it move in a circle around the trash can, you had to push inward on it. Both of those had to do with either accelerating or not accelerating. So we kind of had this idea, this model from it that said, if there's a force on something, it's going to cause a change in its motion, which is just another way to say an acceleration. Speed up, slow down, or changing direction. But then we had to change this a little bit to say, what if there's more than one force? If there's more than one force, then it required an unbalanced force. And the unbalanced force would cause the acceleration. And you could have a situation where the forces were balanced and there was no acceleration. So we also called the unbalanced force the leftover force. So that was kind of what our model was. If you have leftover force, then you're going to get acceleration. We started drawing force diagrams to help us think about that. So we had the weight down for this cart. We had the surface pushing up, which is the normal force. And we had a pretty big push force from the balloon. And so then that would be speeding up. It's speeding up because it has an unbalanced force here, the push, that nothing cancels out. If it was slowing down, we still had the weight down. We still had the normal force up. Those two balanced. But now you had this friction backward that nothing balanced out, so it was slowing down, causing acceleration in the slow down way. When it was going at constant velocity, then that tells you that everything must be balanced out. Normal force in the weight, yeah, but also now the small push that's left plus the friction backward had to also be the same. So this kind of let us link together the motion more exactly to what the unbalanced forces were. And we also talked about the net force, which is a way of saying the unbalanced force, but the net force is the combination of all the forces. So you always have a net force, although sometimes the net force is zero. When the net force was zero, that meant you were going constant velocity or not moving, either one. If you had a net force that was, either positive or negative, that meant you were somehow changing your motion or somehow accelerating. We then realized that force is only half the story, that the other half of the story has to do with inertia. And inertia is the opposition to change or opposition to acceleration. So a force wants to make something accelerate, inertia wants to fight against it. And we measure this with the mass of something, which is usually in kilograms, although sometimes we could do grams. So when we put these two ideas together, that change in motion or acceleration is caused by the net force, the unbalanced force, and also the inertia, that told the whole story. Or another way to write that would be net force like this, and we measure inertia with mass. So we could just write F over m if we remember that's the net force for that case. That was our equation for that. Now remember, Newton had three laws. And I'm not going to test you individually on what these laws are. You don't have to know first law is inertia. Second law is A equals F over m. And running out of space. But third law is that forces always occur in pairs. I'm not going to test you on whether you know which law is which, but you do have to be able to apply all of the laws. Okay, there's a couple other things I want to cover in this. The first thing is the difference between kilograms and newtons. I still get this question a lot. What's the conversion between kilograms and newtons? Remember, there's not really a conversion because this is measuring mass or inertia and this is measuring force. There's really not a connection in regular everyday life between your inertia and force. It's like saying, what's a connection between money and calories? Well, they're different things. There really isn't a conversion to go between the two. If you happen to go to a store that charges you a certain amount for a certain amount of calories, then the store makes a connection. Well, gravity does the same thing. And you remember when we did the Sully kind of demonstration, and we thought of Sully as having 6 rubber bands. So 6 rubber bands here. That was like Earth's gravity pulling down when you're on the Earth. But when you're on the Moon, Sully had 1/6 the gravity, so imagine 1 rubber band. So on the Earth's gravity store converts kilograms to newtons for you, or another way to say it, it pulls down with 10 newtons of force on every 1 kilogram. On the Moon, it's more like 2 newtons for every 1 kilogram. So it's the planet or whatever, the mass that you're on, that makes a conversion between kilograms and newtons. Now there is a conversion from newtons to pounds. So take the newtons, divide by 5, and you end up with the pounds. That is our rule of thumb for this unit that you should memorize, if you haven't yet. So memorize the rule of thumb and memorize that the Earth charges 10 newtons for every 1 kilogram, and those are the things that you need to remember. The last thing that I want to talk about is this idea of terminal velocity, which we hit on a little bit. So just to remind you of that real quick, if you had a very tall cliff, and if something was falling so that it speeds up for part of the time, but then it hits a constant maximum speed at the end, that constant maximum is terminal velocity. So maybe it starts off, at 0 and then it speeds up by 10, but then maybe it only speeds up by 8, and then maybe it only speeds up by 6, and then maybe it's by 4, and then 2, and then maybe it's done speeding up. So it hits that terminal velocity and goes at that maximum speed the rest of the way. The reason why it's hitting a terminal velocity, if you think of the force diagram, is because now air is starting to push up. And the faster you go, the more air is pushing up. Until you reach a point right here, well, I'll do one more, when the air pushes up the same as gravity pulls down. At that point, your acceleration stops, and you hit your maximum velocity, which we also call terminal velocity, and then you just go at that speed. That is kind of the unit in a nutshell. Now there's other pieces. There's Newton's third law that we just went over today, so I'm probably not going to cover that. But that is pretty much the end of the story there. Let me hit stop on this.